The numerical data that I was summarizing about nitration comes from table 16.1. You can take a look at that in detail, but what's perhaps more useful for you is figure 16.11, which gives you the relative activating and deactivating effect of substituents. And what I'm going to begin to talk about now is how we can rationalize and think about and understand these. So, first, we had seen just a minute ago fluorine by inductive effect, that is because of its electronegativity, was a deactivating group. So the halogens are deactivating, okay, but they are orthopara directors. Okay, they're the only deactivating orthopara directors. So they're deactivating by the inductive effect due to their electronegativity. But they're orthopara directors because of the lone pair that's present. So I want to compare a number of these. Let's look at fluorine. If we just think about how fluorine interacts with the benzene ring, we can draw a resonance form where the lone pair swings down, the pi bond swings up, because this carbon, of course, has 8 electrons, and if the lone pair is now going to be shared, it's got to give up 2 electrons. This provides a resonance form. So the lone pair is now on the carbon. That means it has a formal negative charge. So you see, because of the lone pair, the halogens actually donate to the ring, but the donation is overwhelmed by the inductive effect of the halogens. Okay? Fluorine being the most electronegative element, and with others like chlorine, of course with chlorine, you've got the lone pairs, but you're no longer dealing with 2p orbitals like you have on carbon. It's 3p, and so those don't overlap quite as well. Okay? So this, any of the halogens, it could be bromine or iodine here. Now, another class that's very important for us to understand is where you have another heteroatom that's bonded to the ring, oxygen. So oxygen is right next to fluorine. It's almost as electronegative, so fluorine's the most electronegative, oxygen's the second most electronegative, but essentially tied with chlorine. It has an inductive effect, okay? But because oxygen is in the same row as carbon, but it's not as electronegative as fluorine, the mesomeric effect, that is the lone pair donation, gives us this resonance form. And this resonance form now helps us see how the ring is activated. So this is an activator. That means it's more reactive than if it had a hydrogen substituent. By the way, R here can equal hydrogen, alkyl, etc. Okay. So the electron donation from the lone pair dominates in this case, and so oxygen, even though it's the second most electronegative element, because it's on the same row as carbon, it has very good donor properties in this system. So it's an activator and an ortho-para director. Remember we said if they have a lone pair next to the ring, then it's going to be an ortho-para director. Now remember, what's the role of benzene? Benzene in electrophilic aromatic substitution, the benzene is the nucleophile. It's the nucleophile. So if I'm making it more electron dense at the ortho, that means it's a better nucleophile at the ortho position. But look what happens. If I resonate this further, so I'm going to bring this lone pair down. I pointed at this bond because I'm going to make a bond between those two carbons. Now these arrows are communication. They're telling me something. They're telling me what you're thinking, so make sure you catch this. The lone pair, I start the arrow at the lone pair, I point it at the bond because I'm going to make a bond there. That's chemical communication. I can understand that if you write it on your exam. This double bond, I start the arrow in the middle of the bond, which means I'm going to take those two electrons and I point it at that carbon atom because I'm going to draw a resonance form now. You see, in this resonance form, the anion is localized, the anion portion of what's now a zwitterion. That anionic portion is localized on the para position relative to my oxygen substituent. And again, we said that oxygen is an activator and it's an ortho-para director. And so we can see that in our ground state conception of these molecules on the basis of resonance forms, why the ortho and the para position are more reactive. And there isn't what we would call a legitimate resonance form that will put the anion on that meta position. So these are all ortho-para directors because we see the lone pairs activating those positions, making them more nucleophilic. Okay, now, how about deactivator? Well, I already gave you a prelude, if you will, when we were looking at the nitro group. Let me draw a different substituent just to help you see a variety. So these oxygens all have lone pairs, but notice they are not in conjugation with the aromatic ring. The way that it is conjugated with the aromatic ring is like an alpha-beta unsaturated carbonyl compound. That alkene is not nucleophilic, it has umpalong and it's electrophilic because the resonance form with charge separation puts the negative on the oxygen, the more electronegative atom, right? And then the carbocation is over here on the carbon. So this is a deactivator. An electron withdrawing group, we said, is a deactivator of the ring. And we see that manifest from the ground state resonance form. So we're going to actually see two effects that impact activation and deactivation, and directing group effects for ortho-para, and in the case of carbonyl groups, we're going to see that these are meta-directors as well on the basis of the ground state structure. Now, I can draw another resonance form. I can push this pi bond over here to form a double bond there. we get the carbocation at the para position. Now again, if we conceptualize this, in electrophilic aromatic substitution, what is our benzene? Our benzene ring is the nucleophile. And the nucleophile has lots of electrons. So if by resonance this substituent is removing electron density from the ring, which we can readily see by it becoming carbocationic at these positions, you see we have deactivated the para position and the ortho position have much less electron density. And so those positions are deactivated to be nucleophilic because the benzene ring is the nucleophile. In the ring, in the reaction. And so both the para and the ortho position are deactivated. But again, there is no legitimate resonance form for me to draw here that puts that formal positive charge at the meta position. So the meta position is not deactivated for reaction. The para and the ortho are. And in the ortho-para activators, the ortho and the para position are now activated relative to the meta position.